Thank you, Morgan. First of all, I would like to thank the organizers for asking me to give a talk here. It's a great pleasure to be here on this occasion, and I wish Sri Ram many, many happy and active years ahead. So I'm going to talk about a system which is not active. It's a simple equilibrium system, uh, a binary mixture of a lipid and a sterol. And interestingly, this shows a very interesting phase behavior, which is very uncommon in this system. So I thought I will speak about that. And these are the people who did the work. Arif did the X-ray diffraction experiments, and Shabib did the optical fluorescence microscopy, and Anirban Poli did some of the, he did all the simulations that I'm going to present. So we have some observations, and we have some computer simulation which suggests a mechanism for this particular phenomenon that we see. So I need to go through some history because this subject has been around for a long time. So it's not surprising that cholesterol being a major component of cell membranes, people have studied the phase behavior of lipid cholesterol membranes for a very, very long time. And it was known that when you add cholesterol to a lipid membrane, so if you take a lipid membrane, it basically has two phases. It has a gel phase below some transition temperature called the main transition or chain melting transition. And above that, it has a fluid phase. And it is known that when you add cholesterol to the system, it suppresses the gel phase and creates a fluid phase. So by the time you add something like 25 mole percent of cholesterol, you completely destroy the gel phase and you have only the fluid phase. Now, what these people did, what they did NMR spectroscopy and differential scanning calorimetry, and they suggested that in addition to that behavior, which was seen even earlier, at higher temperature, there could be the coexistence of two fluid phases, a phase rich in cholesterol and a cholesterol poor phase coexisting over a fairly extended part of the phase diagram and temperature. But what the technique they used to measure these phase boundaries was differential scanning calorimetry. Not a particularly great technique for looking for phase separation, but so if you take a differential scanning calorimetry trace, if you have a first order transition, you see a very significant peak in the trace. So what they found was they found a significant big peak over the corresponding this transition. And at higher temperature, there was a weaker, broader peak, which they said marks the boundary of the two-phase region. Okay, and therefore they suggested that there could be a fluid-fluid coexistence. After this work, there were many other experiments which again suggested that there is a fluid-fluid coexistence in a binary lipid cholesterol membranes above the chain melting transition. And all these experiments basically use spectroscopy techniques which are sensitive to the local environment, and they don't really look at phase separation in the thermodynamic sense. That is something to keep in mind. So after this, there was theoretical work motivated by these experiments, both thermodynamic and lattice models, something like a non-ideal liquid mixtures, and more microscopic models worrying about the interaction between the lipid and cholesterol. And they also basically came out with a similar phase diagram with a coexistence of two fluid phases at high temperatures. As I said, cholesterol has this effect that it destabilizes the gel phase and it increases the chain order in the fluid phase. Now, if you take a lipid bilayer, in the fluid phase, the chains are in a fluid state, but they are also disordered. When you go to the gel phase, the chains are ordered, but there is also in-plane crystalline order. So there is a coupling between in-plane crystalline order and the chain order of the lipid. So the question they asked was, can you sort of decouple this and have chain conformation which is ordered, but without in-plane crystalline order? And they suggested that it is possible to have this, and therefore you could have these two fluid phases in this system, a liquid ordered and the liquid disordered. And that is the terminology which everyone uses today. It came from this. But I should point out that this was based on experiments which were not really probing to two-phase coexistence. So after this, the liquid-liquid coexistence lipid cholesterol membranes became rather sort of well established. People assume that these systems do show this kind of behavior. Then of course, the story shifts to late 90s. So after the lipid DARP hypothesis were proposed, a lot of people were looking for simple model systems which will mimic raft-like clusters. So basically what you have in model systems would be domains of one phase which is dispersed in the other phase. So essentially fluid-fluid coexistence. So this led to a lot of experiments on model systems looking for fluid-fluid coexistence in lipid membranes. So again, people went back to lipid cholesterol membranes and thought that they could see coexistence of two fluid phases in that system. But people did not find fluid-fluid coexistence in those systems. So this is one of our experiments long ago, where we looked at using X-ray scattering on aligned multilayers, looking at the phase diagram of DPPC cholesterol. So again, what we find, so this lipid has three phases. There's a gel phase at low temperatures, there's a fluid phase, high temperatures, and there is what is known as the ripple phase in between. But in agreement with all the earlier studies, we find that this phase boundary drops down very fast, and you have only a fluid phase when you had something like 20 mole % of cholesterol. The gel phase completely disappears. However, we did not find any evidence for a fluid-fluid coexistence in this system. So if you had fluid-fluid coexistence in the membranes, then these domains in different membranes will interact and come together, and essentially you have two lamellar phases coexisting with two different periodicities. That's what you would expect to see, but we did not see anything of that order. However, we found something else here. We found that cholesterol can induce a modulated phase in the membranes. As the gel phase melts into the fluid phase, there is this modulated phase consisting of stripes of cholesterol-rich domains in the gel phase. So that was somewhat surprising. So this is sort of the model for this. So you have cholesterol-rich regions and cholesterol-poor regions, and these stripe-like patterns lead to a non-uniform height distribution. So there's some kind of a coupling between concentration and gradients in the tilt or curvature, and you essentially end up with these rippled bilayers which have a particular periodicity. And as you increase the concentration of the cholesterol, you find that this periodicity actually decreases. So what it means is that when you add more cholesterol, you create more of these cholesterol-rich stripes in the system, where the width of the stripe does not increase. So as the number of stripes increases, the volume decreases, and essentially you have almost a continuous transition as a function of cholesterol concentration of the gel phase into the fluid phase. So the search for a simple model system for looking at rafts led people to ternary raft mixtures, therefore, because the binary systems do not show this. And these basically consist of two lipids which have very different chain melting transition temperatures. One lipid has a high chain melting transition temperature, the other one has a low chain melting transition temperature. So when you mix the two, you have a temperature range where the fluid phase of one coexists with the gel phase of the other. And now when you add cholesterol, it converts the gel phase into a fluid phase, but these two fluid phases now do not mix, and therefore you have coexistence of two fluid phases. One is now one made up of a lipid with high chain melting transition temperature, the other made up of a lipid with a low chain melting transition temperature, whereas the cholesterol concentration in the two may not be very different. So they are, of course, one is relatively richer than the other, but the difference in the cholesterol concentration is not very high. So this phase diagram was determined by these people using fluorescent microscopy on giant unilamina vesicles. Therefore, you can see a single membrane and the domain formation on these single membranes. And then, so what you can notice here is that this two-phase region, which is confined within this, does not extend to any of these boundaries. So you need all the three components to actually have two-phase coexistence. Now, there's another phase diagram, again of a different raft mixture. The only difference is that these two lipids are slightly different. But more important difference is the phase diagram is quite different now. You do not have just a confined region of phase coexistence. The coexistence also extends to this boundary. For example, the POPC cholesterol boundary also shows a coexistence of two fluid phases. That is because this uses fluorescent anisotropy, which is sensitive to the local environment. And so what they see is not really thermodynamic phase separation in that sense, but what they're seeing are local heterogeneities in the composition, which can lead to different rotational diffusion of the probe molecule. Okay, so this is an important thing to keep in mind, that the phase diagram that one sees depends upon the kind of experimental technique that has been used to determine them. Okay, people very often don't realize this, but it is an important point to notice. That is because we are looking at different things. I mean, so one extreme you have real phase separation with two coexisting phases with an interface between them. Other one could be just heterogeneities, compositional heterogeneities in the system. Okay. So there is a simulation carried of these people where they looked at this region above the chain melting transition region of the lipid system much more carefully. And they found that it actually consists of a heterogeneous composition, which is highly dynamic. Okay. And as you approach the transition from above, the length scales, the time scale becomes slower, and these heterogeneities are more or less frozen in as you approach the boundary. Okay. So they don't see again, there's no fluid coexistence in this system, but there are compositional heterogeneities which are present, which explains all the experimental observations that one has, that are reported in the literature. So we looked at a few other lipid systems to see whether one could see coexistence in any of these. And most of the sterols, which are derivative of cholesterol, or other sterols which are present in plants and things like that, they all show a phase behavior very similar to cholesterol, almost identical actually. However, we found two naturally occurring cholesterol derivatives, which are 25 and 27 oxysterols, which show a very different phase behavior from cholesterol. So the difference compared to cholesterol, the difference is that these have a second OH group at the tip of their tails. Okay, so having this second OH group at the tip of their tails makes their phase behavior in the lipid very different from compared to that of cholesterol. This was published recently, a few months ago. The work has been going for many years, but it got published recently. So the first indication of this coexistence came from experiments, small angle X-ray scattering experiments. So if you look at this region, so what we do is we have an aligned stack of multi-layers. You shine X-rays on it, you get a diffraction pattern like this, which shows a set of peaks as correspond to lamellar periodicity. So at high temperatures here, your diffraction pattern looks like this. You have a single lamellar phase existing here. As you cool down, these peaks split up into two, and you have two lamellar phases with two different lamellar periodicities coexisting in this region. And when you come down below, again, it goes back to a single lamellar phase. So over this region, it should be a closed region, but in this part, what happens is that this molecule comes out of the bilayer. It sort of crystallizes out of the bilayer. So we are not able to probe that. So this would be a closed loop of two-phase coexistence, where you have two lamellar phases coexisting, whereas at higher temperature and lower temperatures, you have a single lamellar phase. Okay. Of course, a phase diagram like this should have an upper critical point and a lower critical point. We haven't probed them in detail, but they should exist. And this is the other system, 27 hydroxycholesterol, which again shows a very similar phase behavior with a region of two-phase coexistence. This part of the phase diagram below that lower temperatures is almost identical to that of cholesterol. Again, at high enough concentrations, the gel phase disappears. And within this, the different phases you see are very similar to that, those you see with cholesterol. Okay. So just since I was criticizing various experimental techniques that you need to use, so we thought of we should look at the system using other techniques. So these are GUVs. So these are GUVs dispersed in excess water. So one problem with multilamellar stacks is that your water content is usually slightly less. So you're not working with in excess water conditions. Okay, so that is one criticism you might have, and therefore sometimes the phase behavior could be different. Whereas in GUVs now you have dispersed this in water, so there's a lot of water around. And again, you see that at high temperature, you see a uniform GUV, a low temperature again uniform, but in between you have a dark patch here, which shows there are two phases coexisting, and the dye that you put in has a preference for one of the phases over the other, and therefore there's a preferential partitioning of the dye. And you see this dark domain. Now, one could also look at the coalescence of these domains with time. So this is over a time period of a few minutes. You find that these domains come together, coalesce, and then become larger. This means that both the phases, both the domains, as well as the phase in which they are dispersed, are both fluid, so that these domains can diffuse around, come together, and coalesce. Okay, so this confirms that this system indeed shows fluid-fluid coexistence. However, the trouble with every experimental technique has its own trouble. The trouble with unilateral GUVs is that when you prepare them, especially multi-component systems, you're not always sure that they have the same composition that you started with. Okay, so we looked at these. These are again multi-layers, very similar to what we use for the X-ray diffraction experiments, but with some dye thrown in. Okay, so you're looking at stack of thousands of layers. And again, at low and high temperatures, you find that you have a uniform phase, whereas in between, you see these domains. Okay, that means there is phase separation, and also that the domains in different bilayers come together and they stack up. Okay, so there is some kind of attractive interaction with these domains in different bilayers. And again, here you can see that with time, you have coalescence, and that again confirms that these are fluid-fluid coexistence. And you can get a phase diagram from this, which looks somewhat similar to that what you did with other technique, not precisely the same, because I mean, one is looking at different things, but the basic features are essentially the same. You have a closed loop region of fluid-fluid coexistence. Okay. Now, closed loop immiscibility is a well-known thing in many binary systems. For example, aqueous solutions of alcohols, amines, and some non-ionic amphiphiles are known to show this. This is a phase diagram of pegged water, and you see that there is a closed region in which there are two phases coexisting, and as you change the molecular weight of the polymer, you get these different regions. Okay, so in all these systems, the reason generally is that, of course, at high temperature everything mixes, and in between there are weak, unfavorable interaction between the different species, which makes the like species come together. And at low temperature, there is always hydrogen bonding. So there is clustering of the two species. So the two species want to come together again at low temperatures because of hydrogen bonding. And that essentially is the reason why the single phase reappears at low temperatures. And of course, there have been lots of theoretical work on this, and this is something which is very well understood. So we want to know what precisely is going on in our system. Is it somewhat similar? So we want to do some simulations. So before that, people have already looked at the difference between cholesterol and this 25-hydroxy cholesterol, how they behave in the membrane. So these are free energy landscapes. So what you do here is that, so along this axis, we are changing the center of mass of the molecule. And along this, we are looking at the different directions. So we hold the molecule in one particular direction and move it across the bilayer and calculate the energy of the system. So this was done by these people. And what they find is that in the case of cholesterol, there is one minimum in the free energy landscape, which corresponds to the cholesterol molecule sitting on the membrane interface with the OH group sticking out into the water, as one would expect. Okay, so that is nothing surprising there. Whereas if you go to this molecule, there are three possible orientations. Now it has two OH group at the two ends. So it can sit like cholesterol, or it can have an inverted orientation, or you can have a flat orientation where both the OH groups are exposed to water. So they found that there are three possible orientations. And of course, there are three minima, and of course, they have different depths typically. So this was what was done by these people. So we thought that we should look at the orientation of this molecule in the system more carefully. So these simulations were done by Anirban, who looked at both DMPC cholesterol and DMPC and 27-hydroxy cholesterol. So these are the details. So basically, we have excess water, and then we can look at the lipid the lipid density, the sterol density, and the bilayer thickness, and also the orientation. So theta is the angle the axis of the molecule makes with the layer norm. Okay, so we can look at these properties and then see how they behave. So this is a joint probability distribution for DMPC cholesterol. So in this case, we find that at all temperature, there is one preferred value of the bilayer thickness, and correspond to that, there is a preferred value of the lipid composition and the sterol concentration. Okay, so there is nothing surprising. So this is consistent with the fact that this system shows only one phase throughout this temperature range. Now, if you go to the other system, what we find is that at high temperatures, we see a situation similar to what we find in the case of cholesterol. Whereas at in-between temperatures, we find that there are two different, so this again, low temperature, again, very similar. The only difference is that low temperatures, it seems to have both cholesterol-like and the inverted, both orientations seem to be possible. Now, at in-between temperatures, we see a coexistence. So there are two preferred values of the bilayer thickness. Correspond to that, there are values for the lipid concentration as well as the sterol concentration and different orientations of the molecule. So at high temperature, there's an orientation. At low temperature, it looks there are two possible orientations. And then the in-between temperatures, all the orientations occur. And we believe that this different, the fact that this molecule can take different orientations in the bilayer as a function of temperature is the reason why this system shows phase separation. So we also find that this phase separation occurs only for a particular range of bilayer thickness. In thinner and thicker bilayer, you don't see it. However, if you take a thicker bilayer and you stretch it, you can have a tension-induced phase separation, because when you stretch it becomes thinner. That's what we think. And so this is also consistent with maybe these molecules can form dimers because they have an OH group at the tip, which is immersed in the bilayer. So maybe they form dimers. This is something we don't know yet. And other interesting thing is that this is also seen with lipids with both saturated and unsaturated chains. Okay, so that is something interesting. And the other point is that the lower boundary of the two-phase region does not seem to change much widely with the different lipids. Okay, so I think I'm running out of time. So to conclude, I think we have, maybe for the first time, have a clear observation of fluid-fluid coexistence in this simple binary sterol membrane system, and seems to be a mechanism where a temperature-dependent orientation of the molecule, which is put in the membrane, can drive this kind of phase coexistence. And in addition to these molecules, we also looked at a few other molecules which have an additional either OH or COH group at the other end, so that they can have this different orientation, and they all seem to show this kind of a behavior. So it looks like this mechanism could be quite general. I mean, that's the impression we have. Biological significance, well, I do not know. The good thing is that the temperature range seems to be compatible and is seen with different lipids with both unsaturated chains also. So maybe, maybe I should say that a wise man once told me that any potential mechanism that you can think of, one can be sure that nature uses it somewhere. You just have to find where. Okay. So if you take that kind of an optimistic view, maybe it may be there somewhere. I do not know. So thank you very much for your.
We have plenty of time for questions.
Do you have any measurement of the tie lines in the phase diagrams? Tie lines?
We can get them, but yes, at present we have not done it, but we can get the tie lines. Yeah. But here the tie lines have to be horizontal because they're two-component system. So then if you know the ends or the boundaries of the phase diagram, the two-phase region, then you know the tie lines have to be parallel to the concentration axis because only two components.
Yeah, the dense phase that you have, that seems to be, it seems slightly different that one would expect for the two-component system. Maybe, I mean,
In what sense?
I mean, the symmetry of that region, if you have the tile line, if you just go along this temperature axis, they seem to vary
See,
slightly
in some
differently.
parts, what I showed you, the right boundary we are not able to determine because the sterol comes out of the solution. Okay, but there are other systems that I didn't show here where we can get the complete closed slope region, and there we have the complete boundary. So the tie line then in that case are parallel to the concentration axis, and so they're very easy to determine.
Raghu, the molecular structure seems to be very close, except one OH group at the end.
Makes a big difference, but
Yeah, but the phase diagram is quite different. Yeah. And then, see, normally is such a sort of anisotropic molecular system, one would expect that there will be miscible really, because the difference is really small, that too only in the tail part. So why such a large difference
in the behavior?
Yeah.
As I said, it's to do with the fact that it can take different orientations. Because it has two, see, the OH group is hydrophilic. Yeah. Okay, and therefore it can come to the surface. And the molecule now taken either decide whether have the first OH molecule at the interface, the second one, or both. And this can depend on the temperature. Depending on the temperature, I said there are 3 minima, and the depth of the 3 minima would be a function of temperature, as you would expect. Okay. So we need to look at those minima more carefully to make sure that what we are saying is completely correct.
In the multilamellar experiments, what you have is, I mean, in principle, what it means is the macroscopically phase-separated state is a sterol-rich lamellar phase versus a sterol. And those two don't have probably exactly the same layer spacing or layer compression modulus.
No.
So that's actually a funny, the full three-dimensional critical point behavior of that is not obvious. Okay. Is there anything of interest there?
Yeah, I think the point is that the bilayer thicknesses are different because the one which sterol has increased its chain order.
Yeah.
So it gets thicker.
Right.
Okay. Now, as you approach the critical point, of course, I mean, they could, but we don't know where the critical points are.
I see.
But it should be worthwhile looking at those.
I mean, it seems to me possibly related to the kind of thing a certain person in the second row studied many decades ago, who's turning around and smiling at me now. So it's some kind of smectic critical point, right?
It is.
Yeah.
It is smectic A because it's a...
These are not tilt phases or anything like that, right? So maybe we can work on that.
Yeah, it is a smectic A. There's no tilt in this case,
For one more. Okay, if no more questions, thank you, Raghu.